seismic ring, right? If we put Z as the surface, then that's exactly the data that we would record. But we can also look at recording the data just kind of from a mental point of view. We can think about recording the data at different depths as well. So this is just the Rayleigh wave field where I've added a variable for depth as well as distance. All right. So this picture basically is a composite, again, of what I just showed you. On the horizontal axis is the amplitude of the Rayleigh wave at depth divided by the amplitude of the Rayleigh wave at the surface. So you can see that at the surface, the amplitudes are the same, and so you get a fraction that's 1. And then we have two different components of the Rayleigh wave, because the Rayleigh wave has motion in two directions. It's got a vertical motion and it's got a horizontal motion. And so you can see that the vertical motion actually goes and increases at the beginning and then drops almost exponentially as it gets steeper, where the horizontal motion actually decreases right at the surface, changes sign with this envelope of decreasing amplitude. So when we talk about the Rayleigh wave amplitude decreasing exponentially, we're really talking about the combination of this vertical and horizontal component. If we look at them individually, they're actually pretty complex. On the vertical axis, what we've got is depth over wavelength. So this is for a particular wavelength or a particular frequency. Okay. So what you can see is that the Rayleigh wave is large up to maybe a half of a wavelength. And beyond that, it really, really decreases in amplitude. So what does that tell you about how deep? Let's say that your maximum, let me give you this. I'm just going to leave it like that for the time being. We can actually take those numbers, though. Actually, let's do that. So let's just say that the Rayleigh wave velocity is about the shear wave velocity. And let's say that the shear wave velocity is, we'll just take a nominal number, let's say 100 meters per second. All right? So, and let's say that our minimum frequency is equal to 5 hertz. And let's say that we can see the Earth down to roughly lambda over 2. Tell me how deep we're seeing in the Earth with that wave. down to 2 lambda. We can generate a curve for any frequency that you want. Okay? It just may not mean it. So you'll see a lot of contractors pointing out, saying, I'll sell you a radial wave. So you say, well, it worked down to 20 meters. Oh yeah, no problem. And my velocity is 100 meters per second. Oh yeah, it'll work great. Or that's it, it'll work down to 40 meters. You say, oh yeah, it works down to 60 meters. Well, it doesn't. All you need is a simple calculation. Okay, so we use these Rayleigh wave surveys, and we're going to talk about them a little bit. They're called multi-channel array surface wave surveys, MASW. And we use them to characterize geotechnical properties. And the simple classifications for soil are basically soil has this velocity of less than 180 meters per second, or any profile with more than 3 meters of soft clay. We go to stiff soil, and the shear wave velocity goes between 180 meters per second and 360 meters per second. Very dense soil, 360 to 760. Rock, 760 to 1500. Hard rock over 1500. Okay, that's just pretty much an arbitrary classification. Doesn't mean that it works everywhere, but it's a start. So if I can measure shear wave velocity through Rayleigh waves at different frequencies, I can get an idea of the lithology, or at least the stiffness of the rock, whether it's soil or rock, as a function of depth. And this could be a lot cheaper than taking a core or drilling a hole. Okay, so this is actually a comparison of actual versus predicted using surface wave data. And you can see that the errors in this case were just a few percent. They actually weren't that significant. And here is a picture of basically the whole technique that I was talking to you before about. And this is the basis of what they call the BS30 method. And those of you that are geotechnical engineers probably know a lot more about the thing than I do. But again, we have a material profile right here. Air, layer 1, layer 2, layer 3. We know that short wavelengths penetrate shallower than long wavelengths. And obviously they're talking about the vertical particle motion here because the amplitude is actually highest below the surface. And from a survey, some way, they measured surface wave velocity as a function of wavelength. Okay, now they didn't tell you how they did it, but somehow they put different wavelengths into the ground at the same place, and they measured the surface wave velocity as a function of wavelength. And this is what they got. And what you need to do in order to get your material profile is you need to take this data and invert it. This is data. You need to invert it for the Earth model. It's called surface wave inversion. The other way you could do it is to run a bunch of forward models and figure out from those forward models what's the best match of the model data to the measured data. So again, we're simply doing inversion either by iterative forward modeling or some kind of computer technique to generate the model from the data. Okay, so this is the thing that we're going to do out in the field, the MASW technique. And this is how commercially, people measure surface wave velocities in a particular area to get a soil profile. The geometry we've already seen before, the assumptions, the analysis, and the results. Okay, so the geometry is just like we talked about in the case of refraction analysis. We've got a source, we've got a series of geophones. We offset the source, the first geophone, a little bit away from the source to make sure that we don't have near field effects. If we don't offset it, we may throw those near offsets away. And then we have a certain array length.